Okay, so imagine if I had 3 points in 3D space, A, B, and C, with the coordinates 3, 1, 1, 4, -1, -1, and 1, -1, 2. I kept the numbers straightforward to make the maths a little easier. If we were asked to create a triangle from those points, so I'm going to connect A and B and C, and obviously I'm going to connect A and C as well to make that triangle closed, but I'm going to do that in a minute. If we were then asked to find out the area of that triangle, um, we could go different directions. We could use 3D Pythagoras, which would get really messy really quickly, or we could be much more elegant about it. I'm just going to pop this up here. So the area of any triangle is given by half AB sine C. Okay. So I'm going to deal with that separately in a minute, but first of all, I'm just going to label this not C, but I'm going to label it theta. Okay, I'm just putting that up there as a reminder. And what I can now do is I can create a vector AB from A to B, so a little vector there, and I'm going to call that little A with a hat on. Okay, and I can create a secondary vector here, BC, which I'm going to call predictably B with a little hat on. So we can start using vectors to work these things out, these values of A, B, and eventually the value of sine C. So what do we do? Well, I'm going to write down the vector AB first, which is going to be equal to B minus A for sort of standard vector calculation. So 4 subtract 3, nicely 1. -1 subtract 1 is -2. And -1 subtract another one is, again, -2 as my first vector. And that's going to be my vector A. Okay, and my second vector I'm going to call BC, which once again is C minus B. And that's going to give us 1 subtract 4 is -3. -1 subtract -1 is 0. And 2 subtract -1 is 3. Okay, so we've got two pretty straightforward vectors, A and B. So what are we going to do with these things? I would be tempted, because we want to know what the value of theta is, or more specifically sine theta is, to use the dot product. Okay, so I've written down the dot product or scalar product relationship. A dot B is equal to mod A mod B multiplied by cos theta, the angle theta we're looking for. So all we need to do is first of all work out mod A. Okay, so we're effectively using 3D Pythagoras on this. 1 squared plus 2 squared plus 2 squared is √9, which is nicely 3. And then mod B, here we have 3 squared plus 3 squared, ignoring the 0, √18, which is equal to 3√2. Okay, so we've got mod A mod B, and we're going to work out what A dot B is, i.e. the dot product. So if you remember, if you know your dot product, it's simply the product of like elements in each of the vectors summed together. So we're going to do 1 times -3, 0 in the center, and -2 times 3, which is -6. So we get -9. So here we have our dot product, and we also want the product of our moduli of each of our vectors. So that's just going to be 3 times 3√2, which is 9√2. So what I'm going to do now is rearrange this, giving us cos theta is equal to A dot B, which you know is -9, divided by the product of mod A mod B, which we now know is 9√2, giving us a really nice simplified -1/√2, or more favourably, -√2/2. Now, you may recognise this. It's actually one of the standard non-calculator angles. It's actually 135 degrees, if we're talking degrees, which we tend to do when we're talking about measurements in space. So we've gone ahead and joined our final side length A to C to create our triangle. Now all we want to do is finalise the area. So looking back at our area relationship is equal to half AB, which is a half mod A mod B in our 3D vector scenario, sine theta. Okay, so we know cos theta is √2/2 or negative. we figured out that sine theta was also, when we squared, we took it away, we've got root 2 upon root 2. So what we've got to do now is just plug things in. So we've got the product of those being 9 root 2. So we're going to half times 9 root 2, excuse me, all multiplied by sine theta, which is root 2 upon 2. Okay, so let's tidy that up a little bit. So we're going to have a denominator of 4, so we're going to have 9 root 2 all over 4, and root 2 is actually 4. So we end up with 9 square units. So a really nice, elegant problem. Whoops, root 2 is in fact root 4, so not 4. So that becomes 9 over 2 square units. Thought I'd leave that in there because I've seen that loads of times. I do it myself, clearly. Okay, so now we're done.